So, and I'll post it to YouTube later. Everybody, sorry
Awesome.
about that. So again, everybody, this is Tony Rice and talking about the James Webb Space Telescope. So Tony, can you continue with that last thought you're at?
Of course. And with your permission, before we jump into Webb, there's something timely and topical that I spent some time writing about last night that I wanted to share regarding a recent SpaceX launch and a number of Starlink satellites that have been lost due to some space weather. So let me come off on that super quick. You may or may not have heard about it. SpaceX has been having a rough couple of weeks. First, a Royal Caribbean cruise ship drifted into their safety zone, and they had to turn around a 24-hour scrub because of it. SpaceX, the Falcon 9, is a little bit different than some other rockets in that it has an instantaneous launch window, meaning the launch window that they have available to them is basically a second long. And it's because of the way the missions are planned and some capabilities of the vehicle itself. They're not able to steer back into a plane because if you think about it, the whole purpose of a rocket is to put that payload into a specific orbit, and the Earth is continuing to turn as time moves on. So if you miss that launch point, unless your vehicle can steer back in and get into the right trajectory, you got to wait till the next day when that launch pad comes back around to that same point. So that kind of hit them up week and a half ago. And the following day, they had to push the next launch off. So that was I believe an Italian satellite that was going into polar orbit. They're starting to launch the polar orbit a little bit more, and that's bad news for you guys. You've been able to see quite a number of SpaceX launches there in Myrtle Beach. We hear from folks in Wilmington and on north that they're able to see those quite a bit too. We're going to be seeing that a little bit less because SpaceX is starting to launch southernly, and both for launches that are going into the 50-some degree inclination, but especially those that need to go into polar orbit. So just something I've noticed over the last couple of launches. But the issue that happened on the launch following this polar launch, it was another Starlink batch. They're about the size of an office desk, satellites that are up there to provide internet connectivity. It was a batch of 49 of those satellites that was to go into orbit. The way they put them into orbit is they put them into a fairly low orbit. They eject the satellites and then start raising those orbits and spreading them out so it fills an entire orbital shell. The idea is to get not quite full coverage of the globe, but pretty close to it. So long story short, they're expecting 40 of those satellites to deorbit. And looking at the data coming from the Space Force that monitors all these things, monitors active satellites, monitors space junk, pretty much everything that's bigger than about 10 centimeters, they're monitoring via radar. 10 of them have already re-entered, and they're expecting another 30 to re-enter. What happened was it's a coronal mass ejection back end of January. And it takes a little while for that to make it to Earth. Fast forward a couple of days, and the CME hits Earth, hits the upper atmosphere, heats up the atmosphere, makes it a bit denser to the point where those satellites that are flying in that low Earth orbit, we're talking roughly 200 miles, 180, 200 miles, something like that. ISS is up at 250. Hubble is up another 50 or so miles above that. A lot of other stuff is up at about 400 miles. So down low, where the atmosphere is quite a bit thicker. Long story short, the CME heats up that atmosphere, causes it to become more dense, and atmospheric drag. The poor satellites couldn't keep up. So they basically lost an entire batch of satellites due to this geomagnetic storm, due to this space weather event. And you might wonder, why didn't we know this ahead of time? Well, the Space Weather Prediction Center, if this is all interesting to you, go Google NOAA Space Weather Prediction Center. They got tons of great information up there, and you can just get stuck on their dashboards for hours and hours. They do measure this kind of stuff, but we really don't know what a particular event is going to look like, more or less until it reaches Earth. The only real sentinel that we have out there is at L1, and we're going to be talking about the Lagrange points here in a minute with the Webb telescope, definitely. L1, about 1 million miles away between Earth and the sun, is where we have a joint NOAA-NASA mission called Discover. Have you ever seen those cool pictures of the moon kind of photobombing, moving in front of the Earth? Those are coming from Discover. Well, the main purpose of Discover is to sit there with its instruments and spot these space weather events. It only gives us somewhere between 15 and, in the best cases, 60 minutes warning. When we really see what what this event looks like, what the polarity of any of these geomagnetic storms are. This is why you can't really predict what aurora is going to look like based on any of these geomagnetic storms until no more than an hour ahead of time. So I just wanted to share that real quick, something that's in the news right now and I found pretty interesting, and then we can jump right into Webb. Any questions before we jump into Webb? Take that as a no, and I will share my screen. And I tend to screw this up, so feedback, Ian.
It looks great.
Are you seeing one slide or two?
I'm seeing one slide, Webb Space Telescope. Let me shrink up this guy. There we go. Yes, it looks great.
Cool. I never know which screen it's going to share. I am not a Zoom expert. So let's jump right into it. So James Webb Space Telescope, named for James Webb. I'll give you some background on him. I had a chance to talk with the Teen Science Council, Teen Science Cafe, they call themselves, up at the Moorhead Planetarium in Chapel Hill, North Carolina, and they were absolutely fascinated with him. We got to learn a little bit more about him. He's an alumni of that university, so we got into that a little bit. Well, one of the questions they had is a question that I've heard a lot about the Webb telescope, and that's why are we bothering with Webb? It took many years to get it built, to get it launched. I mean, even that last week or two when we're trying to get it launched, there's a couple of delays because of weather, because of some tests that didn't go quite as well as they needed to. So why are we bothering with all this? How is this beneficial over the existing Hubble Space Telescope? Don't get me wrong, Hubble's great. Hubble's been called the greatest scientific instrument that was ever created. I think that's very deserved. Webb's going to replace it with that moniker. When you hear some of the scientists say that the James Webb Space Telescope could rewrite textbooks, I don't think they're speaking out of turn there. I don't think they're giving it more credit than it deserves. That remains to be seen, but based on what it can do, that is certainly something that we want to keep an eye on. Webb is different, and we'll see, particularly in looking at the electromagnetic spectrum and what the Webb telescope is focused on. It's different than Hubble. Hubble is far more down into the visible spectrum, whereas Webb is up in the infrared spectrum. And we'll see why that's important in a minute. So it's seeing different things. Its whole goal, every NASA mission has a set of primary mission objectives. Your funding comes from how long you think it's going to take to achieve those primary objectives. These are the basics of the primary objectives. We want to see that earliest light from those earliest galaxies. Looking in the infrared allows us to see behind things that are currently blocked for us in visible spectrum because of dust, looking through nebulae, things like that. That red light pushes its way through a lot more easily. So we're going to be able to see things that we haven't seen before. I have an example of that in a moment. We also will be able to see through water that happens to be in any atmospheres of exoplanets, which is pretty exciting. But the other thing about Hubble is Hubble's been up there a long time. Hubble has been up there for 25 years. It's still going strong. It's not 100%. Hubble does not require any fuel to do what it does. A lot of people don't realize Hubble's in orbit. Hubble's, like I mentioned before, it's in an orbit that's a little bit above the International Space Station, but it's more or less taking glancing blows at whatever it is observing. Webb's going to be in a lot more stable orbit. It's going to be able to stare, if you will, at parts of the sky for a lot longer time period. So it's just different. But Hubble is going to, it has a finite life. Even though it doesn't have fuel on board, it is electrically powered, but that electricity is going not only to the computers and the instruments and things like that, and the radios to get that data back down to Earth, but it's going to a set of reaction wheels. If you've ever seen that experiment at any science museum, will do something like this, where they put a kid on a swivel stool and they give them a bicycle tire and spin it, tell them to tilt it either way. That's basically how a reaction wheel works. That's what's used to point the telescope. And there's a number of them up there in the X and Y axis to be able to point it wherever it needs to point. There's a cheater at a 45-degree angle to that. Those are moving parts, and they're moving pretty fast. Anything with moving parts is going to fail. We've already seen some of those fails. So long story short, Hubble isn't going to last forever. Webb is the follow-on. It's not the replacement. So what I've got on the screen right now is the electromagnetic spectrum. Visible light, you can see, is that little skinny place right there. That's pretty much where Hubble is focused. We've got other missions that are focused in other parts of the spectrum, but see where Webb is focused. Webb is focused in that infrared part of the spectrum and on forward. That is important because, again, you're able to see more things. Here is a good example of comparing visible light to infrared light. This is coming from Hubble. So Hubble, kind of goes into that infrared part of the spectrum a little bit. Webb's going to be able to see even deeper. But the reason infrared is important here is because of redshift. I know many of you are familiar with this, but think about it in these terms. With one of the goals being to be able to see as far back in history as possible, a couple of million years after the Big Bang, hopefully, that light has been traveling a long time. It's going to shift as it travels over these huge distances, as the universe continues to expand. So if we want to see those earliest bits of light, we need to be looking in the infrared. So not only are we looking at infrared to see things that are naturally being produced in infrared, we're really seeing visible light 20, 100 million years ago. That's the reason that infrared is so very important here. And I mentioned that there's other space telescopes. This is something else that kind of blows people's minds. When I first got into this, I knew that there was other space telescopes out there. I didn't know there were so many. Every one that I have up here is basically operational. And the reason there's so many of them is because they all have different jobs. They have different missions that they're trying to accomplish. And as a result, they're looking in different parts of the spectrum. Some of them are more focused on looking for exoplanets. Others are more focused on just traditional astronomy. So you can see Webb is there in the infrared range. There are others that are even in the higher infrared range and on into microwave and radio. They have different purposes. Notice down on the ground, though, I've got a couple of, we'll call them partner observatories on the ground, because they really work together. They work in tandem. And I can't forget Sophia. It continues to be nuts to me that we bought a former Japan Airlines 747 SP, the short version of the 747, cut a hole in the side of the thing, put a movable door on it, and crammed a telescope inside. But the benefit there is Sophia is able to fly above most of the weather, and more importantly, above most of the moisture, or most of the water. So Sophia is able to get some absolutely incredible images, but its benefit is being able to put it somewhere on Earth, whereas you can't move these ground-based telescopes. So with some good planning, we can do things like see occultations. We can place this aircraft in the shadow of whatever is being occultated. It's been done with Pluto a couple of times, which allows you to see those atmospheres of even exoplanets. And Ian, I know your boss has flown on Sophia a time or two, and I love hearing her stories about it. But I just wanted to share this with you to give you a broader view of why Webb is out there. There's been a lot of talk about it in the media lately. It's absolutely earned, but it's part of a bigger ecosystem that is looking across the entire spectrum. So moving on, if I could get my computer to cooperate with me. I want to talk a bit about Mr. Webb. So about 2 years before the Apollo 11 anniversary, I was invited to sit down with the folks at the North Carolina Department of Natural Resources. They wanted to do some planning around the upcoming Apollo 11 anniversary. They're thinking about having some events and things like that, public outreach, and maybe some of the state parks. And I got the chance to sit down next to the person who was responsible for all those cool highway signs that you see. I know South Carolina has them as well, but the historic markers. And we got to talking about North Carolina's place in space history, and a couple of things that they hadn't thought of. Not just astronauts had been born there, but other contributions the state had made. And we wanted to showcase some of those things. And I said, not for nothing, but James Webb's name is going to get pretty big here in a couple of years when we're finally able to launch this telescope. And the question was, who the heck's James Webb? Okay, so he was the administrator of NASA during a really, really critical time. It was during the run-up to Apollo. So we're talking early 60s, basically till he moved on and a new administrator was named right before the first crewed launches occurred. So he was there during that really important time, during the buildup basically of the space race, through Mercury, through Gemini, and on to Apollo. So he's associated with crewed spaceflight. Why the heck would we name a telescope after him? If you look across all of the missions that NASA's had and all of the names that they've applied to spacecraft, it's really, really rare that they put an actual person's name on it. And Denise and I were talking about, last time we saw each other was down at the Cape for the launch of the Parker Solar Probe. That one was super rare because not only do they not name things after real people very often, it's usually goofy acronyms that make more sense to the engineers than to the general public. That was named after a living person, shows how rare he was. But so this NASA administrator that's associated with a crewed program, why the heck would they put it on a telescope? The answer is, throughout all of this, one of the major things that an administrator is responsible for, of course, is setting the direction of the agency. But they're also responsible for driving some of the budgetary things. So where the focuses are placed on where money is spent within the agency. He had a spotlight on him and on his agency during the space race where they could have completely pivoted and focused on nothing but crewed spaceflight, nothing but the manned spaceflight program at the time. And he insisted throughout that run-up, throughout his tenure there, that NASA always spend money on aeronautics and especially on space science, and ensured that it just didn't get lost. That is the reason he was honored with this. The two pictures I've got here, I took at a museum here in Durham, North Carolina, the Museum of Life and Science. Some of his personal effects were shared by the family there. I love the driver's license that was given him by the company that built the lunar rovers that were included in some of the later Apollo missions. And I love that it's license number 1. James Webb was born near Oxford, North Carolina, which if you've ever driven up through I-85, it's a little bit before you get to the North Carolina, Virginia border. Small town. There's a school that was named for his family around there. Back to my story about North Carolina Department of Natural Resources. I said not for nothing, but we've got a pretty important guy here. He really deserves a highway marker as well. And I'm proud to say that we were able to make that happen. So here's Webb. The images you see on the left, those black and white images, the one on the top, those were taken at the North Carolina Museum at UNC Chapel Hill at the Moorhead Planetarium. A lot of the training that went on, of course, happened in Langley in the early days of the space program, the manned spaceflight program. They're in the Tidewater area of Virginia, and then it moved to Houston. But all of the stellar cartography, all of the training that would help the astronauts know where they were in space, and the things that we do behind our telescopes all the time and try to help the public with, that went on at Chapel Hill. And one of the reasons was he was familiar with the first observatory, the first planetarium on a public university campus from his days at UNC Chapel Hill. One of his degrees is from UNC Chapel Hill. And I had to put in a picture of him shaking hands with Kennedy. Found his yearbook photo from the UNC yearbook, had to include that. But this is something I like to think I had a little part in, because I at least clued them in that they needed to look at this. That is Webb's family. They were fun to talk to at this event when we unveiled this highway sign. They were a bit dumbfounded by the whole thing. And it was just dad to them. And here are these people, coming and giving the accolades. That little stuffed toy robot there is the mascot of the North Carolina Science Festival. So he goes along with me and enjoys these kind of things. So let's talk about where Webb is. I mentioned that Hubble is in low Earth orbit. Webb is not. Webb is about 1 million miles away. I'm rounding a lot. And you may have heard that, but one thing that you may not have heard and is not as clear is what that orbit actually is. It's at L2, it's at Lagrange point 2, and the orbit itself is actually quite a bit bigger than the moon's orbit, and it's rotated on its side about 90 degrees. There's a couple reasons for that. Most of it has to do with that this is a very stable orbit. The reason we go out to these Lagrange points is they're kind of like hilltops. If you think about a topography that's got some valleys in it and it's got some hilltops. Each one of these really massive things, like the sun, of course, and the Earth and the moon, they act like valleys. They act like, we call them gravity wells. With anything that is within that well is going to tend to roll downhill towards that gravitational source. These Lagrange points are points of balance, and it allows us to stay there, more or less fixed. We're still orbiting the sun, but more or less fixed, and not have to use very much fuel. And that's not just a great savings of money or whatever. It allows you to extend that mission quite a bit. And I'll talk a bit about mission length and the good news that came out of that. And I'll do that in this right here. Now, I apologize. I'm sure it's really, really jerky. This was developed for some more in-person presentations, but this is the Ariane 5 rocket. So Ariane 5 was selected to launch this beast for a couple of reasons. Number one, it's really the only rocket that could do the job. And I'll show you a couple of numbers to explain why. But this isn't a NASA mission solely, the Webb telescope. It's a joint mission between NASA. Lockheed Martin built the spacecraft, and NASA's prime contractor or managed it there. The European Space Agency was a partner as well, and the Canadian Space Agency is contributing some instruments. One of the primary contributions for European Space Agency is this rocket right here, the Ariane 5. Launched from French Guiana Christmas morning. French Guiana is an interesting place to launch a rocket from. It's got some advantages. It's close to the coast, so we were able to take the rocket as well as the payload there via sea. The Webb telescope actually passed the Panama Canal after it was loaded in, I believe, Long Beach Harbor, following some testing there. But one of the main advantages is it's so close to the equator that you get some free energy simply from the Earth's rotation. Closer you are to the equator, and more of that free energy you get. It's kind of a good place to launch rockets from. But the question that also comes up a lot about Webb is, why was this French designed rocket, European rocket, used to launch this very important asset? Why didn't we use, for example, a Falcon 9? And this helps explain that a little bit. I apologize for the math. I know it's too late on a Thursday night for any math, but bear with me. So I'm calling out a couple of pieces here of an orbit. The whole purpose of a rocket is to put something into orbit. Even when you're going out to L2, when you're going to Mars, when you're going anywhere, you got to go into Earth orbit first before you go anywhere. So the more accurately you can go into orbit, you can do that initial orbit insertion, the longer the life of that mission can be, because any deviation from the middle of that where they're aiming for, it's still what they'll call nominal, but the closer you are to the center of that nominal range, the less fuel you have to use to get yourself back, perfectly on center of that trajectory. And the Ariane 5 has a fantastic performance record when it comes to not just successfully, making it to orbit and not, losing the vehicle and the payload on the pad or whatever, but doing it very, very accurately. So this is just a couple of components of an orbit. Inclination is that measurement of the orbit in terms of that angle between the orbit and the equator. Apogee and perigee, those are measurements of how far out the orbit is from the Earth's surface. The easy way to remember the difference between them is apogee starts with an A, just like away. That's the further one. And then perigee is the one that's a little bit closer. But you can see the numbers that were that I pulled from a couple of documents from the United Launch Alliance that launches a lot of NASA's missions. It's getting ready to launch at the end of this month, early part of next month, the next generation of weather satellites. We're excited about that. Falcon 9, of course, then Ariane 5. These are the numbers that are in their documentation that they give to customers on what you can expect the accuracy of that orbit insertion to be. You just see from the numbers here, Ariane 5 does really, really well. So I talked about the primary mission. If you talk to the scientists, if you talk to the folks involved with this mission 6 months ago, and the question's asked, how long will the James Webb Space Telescope last? The answer was always 5 years. And that's equal to the primary mission. That's what they knew they had to provide in order to meet their objectives. But you always put a little bit more fuel on board so that you can extend the mission. If the spacecraft's still in good shape, if you're able to get to where you needed to get to with any correction burns along the way, you can hopefully use that extra fuel to extend your mission. So they knew that, okay, 5 years, they had to get 5 years. They had enough fuel on board to get 10 with some nominal course corrections along the way to correct any problems with this. A couple of weeks after launch, the analysis comes back on where they actually are in that insertion burns, and turns out we're going to get 20 years out of this. There's even some talk of getting longer that with some other technologies they're working on. But we heard later from a couple of the engineers that were responsible for putting this Ariane 5 together that one of the big reasons they're able to get 20 years and got even better accuracy than when you see up here. They haven't actually published the final numbers, but I've heard they're quite a bit better than this, is not only was the Ariane 5 particularly good at accurately doing orbit insertion, they handpicked the components, like some of the individual engines. They picked the best engine, the one that performed the best, to build this rocket to get the best results out of it. So really got to applaud the effort that was put in by the European Space Agency to get us into the right orbit to really extend this mission. So I'm going to go through, I'll kind of race through this a little bit because I imagine a lot of you have seen it, but I just wanted to give you an idea of the complexity and why this was a bit of a nail biter in the weeks, literally a month after launch, because of all the things that had to go right. What you see right here is spacecraft separation. This is when the spacecraft detaches from the rocket itself. It's still attached to the upper stage. This is doing that initial insertion burn. It's going to separate and begin the process of unfolding. It's folded up in the top of that rocket, in the top of that, surrounded by the payload fairing, because it had to be. In its final form, it's as big as a tennis court. You're not going to stick that on top of a rocket. So it has to be folded up like a transformer here. Everything you're seeing up to this point is all completely automated. The spacecraft is detaching from the launch vehicle. It's extending its solar panels, which had to happen because it was on battery power at this point, charged with ground systems up until the point of launch. It had to get the solar panels out so it basically would stay alive, and then put a very initial antenna out so they can start receiving commands from Earth and moving along in the process. So at this point, we're going to do that mid-course correction burn. It was a simple one, again, because of the accurate orbit. We're about halfway between the Earth and the Moon. So that circle that you see in the lower left-hand corner around Earth, that's not even the orbit of the ISS or of Hubble. It's even beyond that. So, we're well beyond the orbit of Hubble. We're about halfway to the Moon. So it's going to go ahead and start doing its thing. We do that correction burn. We next deploy an antenna, a higher gain antenna, so we can start talking to Earth and be able to send data back and forth. This is going to be the same antenna that the wonderful pictures we're looking forward to seeing are going to start coming down. And then it's time to start unfolding things. So the sunshades, and we're going to see those in a minute, they're there to provide insulation. They're there to block the heat primarily, but also the light that's coming from the sun. The reason we're going to L2, that point 1,000,000 miles beyond Earth, so you go L2, Earth, L1, sun. The reason we're going all the way out there is so that we can more or less put our back with this telescope to Earth and to the sun and block it and be able to operate in a really cold environment. And the way we achieve that cold environment is through these sunshades. They're contained in pallets. We're going to fold the fore one out first, then we're going to fold the aft one out. The next thing that has to happen is the tower that contains the primary and the secondary mirrors, which I'm sure you're all familiar with. If you're like me, you didn't spend a ton on your home telescope, and I've got a light bucket, I've got a Dobsonian, and my primary mirror could use a cleaning. This primary mirror is absolutely pristine, but we got to get it up out of the way so we can start rolling out these sunshades. All these animations were provided by Lockheed, and I think they're great because they really show what was going on. But it's worth pointing out, this is all fantasy. This is not what it looks like in space. It's really, really dark out there, and it's purposely dark. That's the reason we don't have any live video of any of this. We have nothing but animation. You could put a camera out there, but you wouldn't be able to see anything. It would be just completely dark. The next thing that's going to happen, we've already deployed those pallets. We've lifted the tower up a bit. We're going to kick out the solar trim tab. And I bet there's a couple of, you being so close to the beach, there's a couple of folks with boats that can explain why this is important a whole lot better than I can. But basically, this is acting a bit like a rudder. And it's dealing with the fact that the telescope is constantly being pushed by the solar wind. So this device out here helps compensate for that and keep it on course. And the fact that this was deployed so early tells you how important that is and what a factor the solar wind is. So now it's time to unlock the restraints and start rolling them out. And we're starting to uncover the sunshades. I'm just going to push this along. And now it's finally time to pull out those sunshades. So again, these are about the size of a tennis court. Their purpose is to block the heat and to block the light. There's 5 layers there. There's voids between those layers to prevent the heat from transferring from layer to layer to layer, not unlike an insulation in your house. What you see here is one of the few steps that is occurring with a motor. It's drawing this sunshade out using a motor. Most of all this other automated pieces that you're seeing, NASA's learned over the years that the things that are repeatable, the things that work every time, and a lot of the technologies go back to aircraft, to how we release weapons off of a fighter plane, for example, exploding bolts, that sort of thing. A lot of what you see happening here, this movement, is happening because of stored energy and springs that are triggered through exploding bolts and things like that. It's all about what's the most reliable method. Motors tried to keep that to an absolute minimum, but that was one place where it had to be used. I forget the exact number, but there were hundreds of points of failure here. And pretty much it all had to go completely right to get much value out of this. So once this thing was completely deployed and they were in orbit, there was much rejoicing. So next, we're going to tension the sunshades. We're going to spread them apart. We're going to provide those voids that provides that that insulation, and we're going to stretch these things out so that they can do their job. They can provide that insulation. This is all being triggered from the ground, and they took their time doing this. These things were done day by day by day. They were trying not to work them 24 hours. COVID was a factor there as well, but they wanted to be able to run the checks and make sure that they were ready for the next part of the deployment. So now we're finally, we've got our shades set up. It's time to start looking like a telescope. So they're going to push this secondary mirror out and locking it into place. This is where some sighs of relief started happening. Technically here it was usable. We want the primary mirror completely deployed, but it's more or less usable here. This secondary mirror, I believe it was about 5 foot across. It's circular. It is gold covered as well. Gold is a substance that reflects infrared light particularly well. The hexagonal mirror segments there, they're also covered in gold. They also have actuators behind them. And next we'll go ahead and deploy the primary mirror. Those actuators allow the shape of the mirrors to be controlled. And if you remember back, the problems that we initially had after the Hubble Space Telescope was deployed, having some ability to make corrections to the optics remotely is pretty important, because we can't go service this thing. It's out there. We couldn't reach it if we tried, particularly with a crewed mission. So at this point, we're bringing the rest of those mirror segments in place, and we're just about a real telescope here once those are locked in. So the next thing that's got to happen is we got to go into that orbit that I was showing you earlier, that orbit out at L2. And we're not quite at L2 in this orbit. The way it was described to me is, picture that well, picture a curve down to a point where the Earth is at the bottom and its gravity is drawing everything down there. The Webb telescope is going to be kind of pushing up on the edge of that well, and it's constantly going to be going uphill a little bit. So about 4, maybe 5 times a year, it's going to fire those engines just to push it back up that hill a little bit. You don't want to go over the other side of that hill, because then you continue to move and you're not in the right place, and the mission's kind of lost at that point. But constantly pushing up the edge of that hill is a great way to keep it into orbit. When it launched from Earth, it didn't go straight out to L2 either. It was diving down a little bit to go into that circular orbit that you see there. So what's next? We're in this cooling phase right now. We're a month, 2 months after launch. We're fully deployed. The cooling phase is there because these instruments have to operate at an incredibly cold temperature to be able to have the sensitivity that's needed. We're talking approaching absolute zero. And that's why one of the main reasons we went out to L2, to be able to get away from the heat of the sun, to be able to put that sunshade facing back towards Earth to block that heat and to be able to operate in that really, really cold environment. We're not going to see images from this for a while. They are going to begin testing out the telescope. They've announced what the first target is going to be. I believe it is in Ursa Major. I can look that up before we go, because that might be kind of a fun thing if it happens to be up when you're doing a public observing session, to be able to point to this particular star. And it's well within reach of moderate sized telescope, if I remember right, if I remember the magnitude correctly. We're not really going to image it so much as it's being used as a target to verify the telescope. So commissioning is going to take quite a while. And aligning the telescope is going to take a little while. So it's going to be, a good 180 days before we really see some of those first images. Something the Space Telescope Science Institute that's responsible for maintaining this project, maintaining this, operating the Webb telescope, learned from their operation of the Hubble telescope is it's really easy to forget and get totally focused on the science here. Forget that these things, they have a great attraction to the general public. And the images that are coming raw off of these telescopes, well, number one, they're all monochrome, because that's how you get the best resolution with these instruments. They do have the ability to create some full color images with Hubble. So they had to pause and remember to spend some time getting some of those public engagement images. I'm sure that Webb is going to remember the same thing. Going to be a little bit different because, again, we're not in the visible light. So they're going to have to be shifted a little bit just to be able to see something. But I'm looking forward to seeing some really cool pictures coming out of this. And I was trying to hit 8 o'clock, and I think I almost did, because I suspect we might have a couple of questions. I've been running my mouth for half hour, 45 minutes. Is anybody still there?
Yeah, absolutely. We're still here.
Cool.
I'm sorry, and you might have said this already, it's Denise. What is the very first data that we're expecting to get back from this? Do you have any information on that? I don't know, or you might have said something already.
I don't, unfortunately. That first target in Ursa Major is the only one I've heard about. I know that the call went out for professional astronomers to put in bids, to put in papers, basically competing for time. And it's the same process that's used with the Hubble Space Telescope. It's a limited resource. There's only so much time that's available. I don't know if they've made those selections on what the first science targets will be yet. I'm sorry, I don't have that.
Yeah, question. Tim Kelly here.
Yes, sir.
Can't wrap my head around this. How do you know you're looking at some of the very first light coming from the first stars?
It's in large part about that wavelength. It's because the time that has passed and what we know about the expansion of the universe tells us that we're looking in the right wavelengths. And Mr. Astronomy Professor, feel free to jump in and save my bacon on any of these questions.
Yeah, so fundamentally that's it, right? So what you're seeing is the light get red shifted because of the expansion of the universe, right? So we know about where it should be. Plus you got the age of the universe, right? As you're seeing things farther and farther back, right? So the idea is that originally in the universe, there were originally very early stars that were very, very massive and very, very bright and lived very, very short lives. And we're trying to understand, technically they call population 3 stars, but we're trying to understand what those are all about so we can understand the early universe. But nothing is capable of even seeing any signs of those right now. So that's one thing. Webb is designed to capture what we think is the signs of these earliest stars, right?
So I'm a ham radio, so I'm thinking what you just told me is as the universe expands, those wavelengths get long.
That's exactly correct. Exactly correct. And they get longer and longer as they stretch, right?
And we don't have any telescopes, space telescopes, that are focused in that section of the spectrum until Webb. So that's the big key here, is now we can see this range and that stretched light going back to that time.
By the way, what Tony's showing is a very cool app called DSN Now, which shows you all the NASA telescopes and what they're currently talking to in real time.
And you can see Webb is talking to a couple of the dishes in Madrid right now. Webb is a hog, is a dish hog. More often than not, when I tune into this, I see JWST popping up because they're actively talking to it. So this right here tells me that they are probably deep into pulling data on and off of there for some of that initial commissioning of the telescope. And down the bottom we can see HPC, is that New Horizons? That is, yeah, that's New Horizons. So that's our favorite mission that gives us or gave us beautiful pictures of Pluto and has moved on to other things in the Kuiper Belt. And looks like it was getting ready to start talking to a couple of Mars missions. The only reason I bring this up is just to kind of bring it back to current times and see that we are actively talking to this mission right now and working on getting it fully commissioned. More questions?
So how can you circle a point in space, like, that Lagrange point L2? How in the world are you circling nothing, really? How do you lock on that point?
So that point is, a single point in space. It's non-moving, other than the fact that there's, slight variations in the orbits of the planets. Like I say, it's that point of balance. The way it was described to me, and I wish I was there so we could grab some physical things and play around with it a bit. Maybe even a gravity well isn't the way to think of it. Think of a very bowl-shaped bowl. Forgive me, but not all bowls are bowl-shaped. Very half of a sphere.
Okay.
Think also of maybe a skateboard park, maybe a kid on a skateboard in an empty swimming pool, and riding the edge of that pool right there on the coping and circling it. And he or she is not actually, there's not a physical point that they're touching or they're orbiting, but there's this kind of imaginary point. That pool always wants to pull them down to the bottom. That's the gravity at play. But by giving a little oomph, and in the case of the skateboarder, that's the foot off the skateboard, touching the pool and pushing them up in that circle. And in the case of the spacecraft, it's those engines, and it's burning that fuel to keep it moving in that in those not small circles, they're huge circles in this case. It's just a really good place in space because of that equilibrium. Because it's not being pulled in either direction. We're purposely just a little bit on this side, closer to the Earth. So if those engines did not fire, we would eventually be pulled into Earth's gravity well, but it works out really well that way. I should point out too that the spacecraft has engines, but they're all facing on the backside. So they're pointed back towards Earth and the sun. It's particularly amazing that they were able to get into this orbit when you think about the fact that they didn't have any way of slowing down. Normally, when you're going to Mars, you're going to any other planet, the plan is you go into Earth orbit, you go into a trans-injection orbit, be trans-lunar orbit or trans-Mars orbit, where you fire your engines and you get going fast towards whatever body you want to get to. Well, if you don't slow down, you're going to keep going past there. So most missions will fire their engines, either rotate around or maybe have the engines pointed in such a way that they'll fire their engines and slow down so they can get going just the right speed to be able to go into orbit around that body, around Mars, around the moon, whatever. It's how we went to the moon with the Apollo missions. We pointed the spacecraft towards the moon. We went fast enough to get there. We fired the engine, slowed down to be able to go into lunar orbit. That's not how James Webb got into this L2 orbit. It couldn't slow down. Its engines are facing back towards the Earth. So the amount of planning and execution and pulling this off, quite frankly, that went into this, to be able to put that thing in a injection orbit that would have it, think again of that bowl, of that swimming pool, crawling up the edge of that swimming pool. As you watched, they had a really nice, actually, let me bring that up real quick. They offered a nice interface to show what was going on with the telescope. And one of the measurements over that first week or first month or so before they got into orbit was, okay, good, there's still data there, was speed. And they pulled the speed reading off, but this is another great website you can go and look at. Watching that speed go slower and slower and slower as they got closer to L2, that orbit was designed perfectly, that trajectory was designed perfectly, so it just kind of creeped its way and fell into that L2 orbit. I don't know if I answered your question or just rambled for 5 minutes, but it's all about planning, and it's all about staying on that edge of that bowl, if that makes sense.
That makes sense. Thank you.
And while I've got this up, take a look at some of these numbers. Let me embiggen this some. So you can see the 4 points that there are. Well, actually, there's a couple more than now. They've turned some more sensors on. Sensors on the spacecraft. They talk about the hot side and the cold side. When we think about space, we think about space being an incredibly cold place. It's incredibly cold in the shade. Otherwise, you see that hot side? Now, one of those sensors is reading 95 degrees out in the vacuum of space. But we need to, on the cold side, get it down to, pushing -400 for those very sensitive instruments that are looking at that infrared spectrum to be able to operate properly. And this is going to be out there for quite a while. It will, I think they're going to keep this website up so you can see what those temperature readings are. And I bet they'll add some more instruments over the time, or more readouts over the time. Ooh, this is new. Let's see what this is doing.
This website open to the public?
Yeah, Tony, I think the question is this website open to the public? I think it is, right?
Absolutely. Yeah. web.nasa.gov.
Now, Tony, we're strictly looking in the infrared, so I guess that's going to tell us more about the beginning of the universe, but what about exoplanets? I guess would that be a different wavelength? Dark matter, a different wavelength? Can we learn about all those kinds of things too, as well with this?
Exoplanets are a big part of the primary mission, in large part because that infrared light is going to pass through particularly atmospheres of exoplanets, which is of great interest. We really want to learn about those exoplanets that do have an atmosphere, and not just that they have them. We want to know what they're made up of. Learned so much with that New Horizons mission simply by flying that spacecraft behind Pluto and putting the sun directly behind it. So we had that light streaming through the atmosphere there, and that's where the spectrometers are able to determine what the chemical makeup is of the atmosphere. We can do some of that with Webb as well, again, because it's able to punch through those atmospheres, even the thicker atmospheres of some of the gas giants that are out there. So not just the terrestrial ones that have atmospheres. We should be able to tell quite a bit about the atmospheres of some of the gas planets as well. Again, because it's working in the atmosphere or working in the infrared. So if you get nothing out of our time tonight, other than Webb is cool, Webb is giant, Webb is out there, it's at L2, is its reason for being is infrared. So this is fun to play with. This is Webb in real time. This is all based on telemetry coming from this spacecraft, and NASA has a couple of really cool tools. And I bet Ian can set you hip to Eyes on the Solar System, or Denise. This is just grand fun to play with. But it's so weird being out here so far beyond and seeing a spacecraft like this. But yeah, this is all publicly available. You can go and play with this to your heart's content. Web.nasa.gov is one, eyes.nasa.gov, EYES. And then
Say that again, please.
so web, WEBB.nasa.gov would be the one I'm on right now. And then eyes, EYES.nasa.gov will give you access to something like I have up here that will let you look at just about any spacecraft out there. And it's basically a browser for the solar system. It's a really neat tool. But you can also get to that deep space network that I was showing you earlier with the real-time view of what's talking to us. More questions?
Of course, Kevin will be very glad you plugged his product. So,
okay, Kevin's the man, and they've really improved that over the years. They've changed out the engines and such on it, so it's a little more performant. The fact that I can run it while I'm running Zoom at the same time, that's pretty amazing. Zoom's a pig.
Does anybody else have any questions?
What's this one here?
This is Deep Space Network now.
Yeah.
This is this is a representation of what you see up on the big screens in basically mission control at JPL that's talking to all the robotic missions. Very unique capability, and you'll see other countries' missions pop up on this. Everybody but China and Russia, I should say. You'll see missions from Japan, from the UK, from most recently United Arab Emirates will show up on here. India has some missions that show up on here because basically this is the only system that can reach out beyond the orbit of the moon. China has some limited capability of talking to some of their missions. They put a relay satellite basically out at L1. I was speaking of earlier, between the moon and the sun, to be able to talk to their missions on the far side of the moon. But this is a very unique capability right here. We're still talking Webb, and we're talking New Horizons. You'll even see some of the older missions from back in the 70s will still show up from time to time on here. The ones that are run on 8-track tapes that still somehow function. Go on, more questions.
Okay, it looks like no more questions. So I'd like to thank Tony for taking the time to present to us and telling us, hopefully, things that you didn't know. I learned a few things, so I hope everybody else learned a few things about the James Webb Space Telescope. I was telling Tony we'll have to get him down here in person someday as conditions loosen up. We'll get him down sometime to address us in person here at Coastal. So,
if y'all are interested, one of my favorite things to talk about is launch weather forecasting. Is all the things that all the questions have to be answered on the ground before we launch a rocket. The fine folks with the Air Force, now Space Force, that take care of that, and what happens when you don't do it right. Blowing up rockets is always a fun thing to talk about. I'll just throw that out there as an idea.
Well, we'll definitely, we're gonna definitely hit you up for some more presentations, so don't worry
Cool.
about that.
Happy to do it. Yeah, we got plenty to pick from.
All right, well, thanks, Tony, for joining us.
Thank you.
Good
Appreciate
meeting
it.
everybody. Good seeing you, Ian. Good seeing you, Denise, again.
Thank you. You're very good. Very good. Hey, can I sort of, I mean, there's parts of it that I like to show to my students, not the whole entire thing, but certain parts of it. If there's some way I could get a copy of your presentation. I don't know if you
Yep.
give it or not, but
Yeah, I may already have it up there on SlideShare.